Hi guys, in today's video we're going to take a look at types of intermolecular forces, looking at London forces, permanent dipole-dipole interactions, hydrogen bonds, the properties caused by these forces, an exam style question, and finally a summary.
So let's begin by having a look at an introduction to intermolecular forces. You may have previously come across intramolecular interactions. These act within molecules. So atoms within molecules are held together by chemical bonds. You may have met ionic bonds and covalent bonds, which are an example of these intramolecular interactions. In today's video, we're going to have a look at intermolecular interactions, and these are the forces of attraction that act between molecules. These are non-bonded interactions, unlike our ionic and covalent bonds. They do not involve the transfer of any of electrons. They are a result of the constant and random movement of electrons within shells of atoms. So let's take a look at the types of intermolecular forces that we're going to have a look at. There are three main types of intermolecular forces. The first is London forces, the second is permanent dipole interactions, and the third are hydrogen bonds. We're going to begin by having a look at London forces. London forces are proposed by German physicist Fritz London, and that's where they take their name from. Now, rather than our electrons existing statically within orbitals, they're constantly moving within the clouds of charge. So you can see here we have our tiny central nucleus and we have our yellow electrons whizzing around within their orbital. Now, on average, the electron density will be symmetrical. But at any one given moment, it's likely there are more electrons on one side of the atom than the other. And as a result, what we'll see is that temporarily the charge is unequally distributed, and there's what we call a temporary dipole. In our example here, you can see there are more electrons on this side of the atom. As a result, as you can see down here, this side will have a more negative charge. So temporarily, this side of the atom is negatively charged, and this side positively charged. Well, like dominoes, the temporary dipole can induce a temporary dipole in its neighbouring atom. So you can see here a temporary dipole where we have the negative on this side and the positive on this side has induced a dipole in the neighbouring atom and its neighbour, and this goes on to induce temporary dipoles in the neighbouring atoms. Now the two dipoles will be attracted to each other. The temporarily positive end of one molecule will be attracted to the negative end of another. Now these dipoles are constantly being formed and destroyed, but overall what we observe is that the atoms are attracted to each other. So we've looked at London forces on an atomic scale, but it's important to understand that London forces occur on much more than just an atomic scale. They occur on a molecular scale too, and what you'll see is that London forces occur between almost everything. That's in addition to other intermolecular forces of attraction that we'll look at later in this video. So now we've had a look at London forces, that's induced dipole interactions, let's have a look at permanent dipole interactions. Well, we see the same interactions between molecules that have permanent dipoles. Here we have a chlorine covalently bonded to a hydrogen. The chlorine is the more electronegative element, and therefore the shared pair of electrons is held closer to the chlorine, resulting in an overall permanent dipole. There's a slightly negative charge and a slightly positive charge on this molecule, and you'll see I've shown that here. Now, if two molecules of HCl, hydrogen chloride, are aligned correctly, then they will attract each other. The positive end of one will be attracted to the negative end of another molecule. Now, it's important that we understand that as the molecules are randomly and constantly moving, they do not always align. If the positive end is aligned next to another positive end, they will in fact repel each other and not experience an attraction. So let's just recap what we've discussed so far. We've looked at London forces and permanent dipole interactions. We know that London forces occur when temporary dipoles induce dipoles in neighbouring molecules. They occur between an induced dipole and an induced dipole. Now we know that our permanent dipole interactions are when permanent dipoles are attracted to the opposing charge in other permanent dipoles. They occur as an interaction between permanent dipoles and other permanent dipoles. Now it's important for us to appreciate that our London forces, which occur between induced dipoles, will always be aligned. That's inherent in their nature. In inducing a temporary dipole in a neighbouring atom, that atom or molecule is already aligned in the correct way to experience an attraction. However, our permanent dipoles align much less frequently, and when averaged out, these interactions occur on a much smaller scale. So, on average, these interactions will be weaker across a number of molecules. So now we've had a look at London forces and permanent dipole interactions. Let's just take a step back to have a look at some of the terminology that we often use. Dipole-dipole forces is a term that's used to encompass both permanent dipole interactions and permanent dipole-induced dipole interactions. It's perfectly possible for a molecule with a permanent dipole to induce a dipole in an atom or molecule neighbouring it. So let's go ahead and summarise the terms we've used now. We've seen our London forces that occur between an induced dipole and an induced dipole. Our dipole-dipole interactions, which encompass the permanent and induced dipole interactions and the permanent dipole interactions. We can take a further step back to look at another umbrella term used. This is the term van der Waals forces. Van der Waals forces is used as a further umbrella term to encompass both London forces and both of our dipole-dipole interactions. The use of so many terms may seem a bit confusing, but it's important for you to appreciate that London forces occur between two induced dipoles. Dipole-dipole interactions encompass both our permanent dipole interactions and our permanent dipole-induced dipole interactions. So far, we've had a look at our London forces and our permanent dipole interaction, looking at the terminology we use to reference these. Hydrogen bonds are our third and final type of intermolecular force of attraction. They are strong permanent dipole forces of attraction that occur in a special situation. They occur between an electron-deficient hydrogen. Our electron-deficient hydrogen arises when a hydrogen is bonded to a more electronegative element. So you can see here we have our hydrogen bonded to oxygen. Oxygen is more electronegative than hydrogen. It will hold the pair of electrons in the covalent bond closer to the oxygen. Generally, the elements that when bonded to hydrogen result in an electron-deficient hydrogen are oxygen, fluorine and nitrogen. And you can see here we have our hydrogen bonded to an oxygen. The oxygen is slightly more electronegative and the hydrogen slightly more positive. So that's the first component of our special situation. The second is the lone pair of electrons on a highly electronegative atom on another molecule. Again, that electronegative atom can be either oxygen, nitrogen or fluorine. So you can see here we have our oxygen with two pairs of lone electrons. So what does our hydrogen bond look like? I've represented it with a dotted line. You can see we have our hydrogen bond forming between an electron-deficient hydrogen. You can see our hydrogen is bonded to an oxygen, which we know is more electronegative, and the lone pair of electrons of an electronegative element on a different molecule. In this case, our oxygen. I'm sure you will have spotted that these molecules are in fact molecules of water, H2O. So now I've had a look at this classic example of hydrogen bonding. Let's have a look at some other examples. First, let's remind ourselves in what situation our hydrogen bonds can occur. They occur between an electron-deficient hydrogen. That's a hydrogen bonded to a more electronegative element, usually fluorine, nitrogen or oxygen. And it occurs between the lone pair of electrons on a highly electronegative atom on another molecule, again being fluorine, nitrogen or oxygen. So let's have a look at the example of ammonia. We have our hydrogen which is bonded to a nitrogen, an element we know that is more electronegative. And the hydrogen bond is forming with the lone pair of electrons on the nitrogen of another molecule of ammonia. Interestingly, all compounds containing a nitrogen-hydrogen bond are able to form intermolecular hydrogen bonds. So let's have a look at our example, which includes fluorine. Our example is hydrogen fluoride. Now, interestingly, the only fluoride-containing compound with intermolecular hydrogen bonds is hydrogen fluoride. And you can see we have our hydrogen covalently bonded to a fluorine, a more electronegative element, forming our hydrogen bond with another molecule of hydrogen fluoride. So now we've had a look at some interesting examples of hydrogen bonding. Let's go back to have a look at our initial example of water. As we know, hydrogen bonds exist between our water molecules, and you can see we have two water molecules here, and this hydrogen bond is forming between the hydrogen on one molecule and the lone pair of electrons on the oxygen of another molecule. These hydrogen bonds that occur between our water molecules give water some really interesting properties. The first is that the solid form ice is less dense than the liquid form water. This is a property you'll be very familiar with in seeing that your ice floats in your glass of water. This happens because many hydrogen bonds form between water molecules in our solid ice. Although these form in liquids too, they break and reform easily as the molecules move around. Molecules of water move around in the liquid form. The hydrogen bonds that form in our solid ice hold the water molecules apart in a fixed position, giving ice an open lattice structure of rings. And it's this open lattice structure that allows ice to be less dense than the liquid form of water. The other interesting property that the hydrogen bonding allows for is an unexpectedly high boiling and melting point of water. This is because the hydrogen bonds are much stronger than other intermolecular forces, such as our London forces. And these strong intermolecular forces have to be overcome before melting or boiling can occur. The last is that water has a high surface tension. The lattice is strong and flexible, and as a result, insects are able to walk on water. So now we've covered all three types of intermolecular forces of attraction. Let's just quickly recap. We have our hydrogen bonds that occur between an electron-deficient hydrogen and the lone pair of electrons on an electronegative element. We have our van der Waals forces of attraction, which encompass both London forces, which occur between an induced dipole and an induced dipole, and dipole-dipole interactions, which encompasses both permanent dipole interactions and induced dipole, permanent dipole interactions. So now we recap the different types of intermolecular forces. Let's take a brief look at their relative strengths, because the three main types of intermolecular forces differ in their relative strength. The weakest form of intermolecular force of attraction are our London forces. Then we have our permanent dipoles, and the strongest is our hydrogen bonds. The type of intermolecular force affects the boiling points. Now we can see the effect of hydrogen bonding on boiling points by looking at the boiling points of the hydrides of elements from groups 4 to 7. And here we have that shown in a graph. We can see trends within this graph. We're going to take a closer look at some certain trends. First of all, let's take a look at the boiling point of our noble gases. Our noble gases are shown here in yellow, and the trend that we see is a gradual increase in the boiling points. So why do we see this gradual increase in the boiling points? Well, only weak van der Waals forces of attraction exist between our noble gases. Now, the van der Waals forces of attraction increase as the number of electrons increase. So the boiling point increases down the group. If we have a look at the boiling points of water, hydrogen fluoride and ammonia, we'll see higher boiling points than expected. This is because all these substances contain hydrogen bonding. They have a higher boiling point than other hydrides within their groups. Now, if only the weak van der Waals force of attraction were acting, the boiling points would be much lower. However, the strong hydrogen bonds allow for these higher boiling points that we observe. Which molecules form hydrogen bonds? We're given hydrogen sulfide, hydrogen, ammonia, and boron trifluoride. Now we know that hydrogen bonds occur between an electron-deficient hydrogen, that's a hydrogen that's bonded to an electronegative element, usually fluorine, nitrogen or oxygen, and the lone pair of electrons on another electronegative element of another molecule. So if we have a look at each of our options, we can see which one is most likely to form hydrogen bonds. In our hydrogen sulfide, we don't form hydrogen bonds. Sulfur is not one of the elements that when bonded to hydrogen is electronegative enough to allow for hydrogen bonds to form. So we can eliminate that. Although our diatomic hydrogen may first sound like it's the correct option, our hydrogen is not bonded to a more electronegative element, and so no hydrogen bonds form between the molecules of hydrogen. We know that nitrogen is one of our elements that when bonded to hydrogen is electronegative enough to allow for hydrogen bonds to form between molecules. So this is a possibility. Looking at our last option to eliminate it, if possible, boron trifluoride. Well, boron trifluoride does not contain any hydrogen, although it does contain the electronegative fluorine. But between our molecules of boron trifluorides, only dipole-dipole interactions will occur, not hydrogen bonds. And for that reason, it's our ammonia and option C that is the correct answer. Moving on to question 2. Which of these molecules has permanent dipole-dipole attractions between molecules? So we know that for permanent dipole-dipole interactions to occur, there has to be an overall permanent dipole, and the molecule cannot be symmetrical. So we can go ahead and eliminate the options which are symmetrical. We know carbon tetrachloride will have a tetrahedral shape and will therefore be symmetrical, and so it cannot be option A. We know that C2F4 tetrafluoroethylene will also have a symmetrical shape, as we have 2 carbons, which will be bonded as such, with 4 fluorine atoms, bonded here, 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 and here. So we can eliminate option B. Looking at option C and D, we know that carbon dioxide has a linear shape and will therefore be symmetrical, and therefore will not have an overall permanent dipole. And as a result, we can see that option C is the correct answer and will have permanent dipole-dipole interactions, as a permanent dipole will exist. We're now asked to explain for 3 marks how these forces of attraction arise, how these permanent dipole forces of attraction arise. So how do we answer this question? Well, first of all, we explain what a permanent dipole is. A permanent dipole exists across molecules, meaning there's a charge difference across the molecule. There is a slightly positive end and a slightly negative end, and as a result, when correctly aligned, the opposing charges on molecules attract. The molecules therefore experience an attractive force. Here, for our first mark, we explain that a permanent dipole exists, and as a result, we have a charge difference and a slightly positive and negative end. And for our third mark, we explain that as a result, when correctly aligned, the opposing charges will attract, and the molecules will experience the attractive force. Question 3. Water is responsible for the development of life on Earth. There are several special properties of water that help it sustain life. In terms of intermolecular forces, explain the following. Ice is less dense than water. This is a really unique and interesting property of water. The solid form, ice, is less dense than the liquid form, water. And this is primarily because water molecules hydrogen bond to each other. Now in liquid, these hydrogen bonds break and reform. Whereas in solid water, we have these fixed hydrogen bonds forming an open lattice. There's large areas of open space in between these rings. Now when the ice melts back into the liquid form, the ring structure is destroyed, this lattice structure, and the average distance between the molecules decreases. This unique property of water is primarily due to the bonding involved. Water molecules hydrogen bond to each other. Now in our solid form, we have these fixed hydrogen bonds that form an open lattice. The structure creates large areas of open space inside these rings of our lattice. When the ice melts to form liquid water, the ring structure is destroyed and the average distance between the molecules decreases, causing an increase in the density. So I can summarise that in our ideal answer. I've explained that water molecules hydrogen bond to each other. Solid water has fixed bonds forming an open lattice. However, in liquid water, these hydrogen bonds break and reform. The first mark is awarded for explaining that in solid water we form this open lattice of hydrogen bonds, and the second for explaining that in liquid water the hydrogen bonds break and reform. Part B. In comparison to similar molecules such as H2S, hydrogen sulfide, water has high melting and boiling points. So, in order to explain this, we need to remember that molecules of water form hydrogen bonds with each other, whereas hydrogen sulfide only has dipole-dipole interactions. The hydrogen bonds are much stronger than those weaker dipole-dipole interactions. I've explained that molecules of water can form intermolecular hydrogen bonds, whereas hydrogen sulfide molecules only have dipole-dipole interactions. Hydrogen bonds are much stronger. The first mark comes from identifying the intermolecular forces of attraction between our water molecules and comparing that to the hydrogen sulfide, and the second for explaining that hydrogen bonds are much stronger. In question 4, we're asked to explain the differences in boiling point of the following molecules. We're given the boiling point of ammonia as minus 33 degrees Celsius, hydrogen sulfide as minus 60, and that of methane as minus 162 degrees Celsius. Now this is due to the different intermolecular forces of attraction. We know that ammonia forms intermolecular hydrogen bonds. We know that hydrogen sulfide has dipole-dipole interactions. And methane has London forces. We know that hydrogen bonds are the strongest intermolecular force of attraction, followed by those dipole-dipole forces of attraction, and finally London forces. And finally, that less energy is needed to overcome the weaker forces. In this case, the London forces are the weakest, explaining why the boiling point of the molecules differs in this way. 1 mark is awarded for identifying the type of intermolecular forces of attraction in all 3 of our molecules. A second for explaining that hydrogen bonds are stronger than dipole-dipole interactions, which are stronger than London forces. And a third for explaining that less energy is needed to overcome the weaker forces of attraction, explaining why the boiling points are as they are.
Hey guys, I hope you're enjoying the video. If you're looking for an amazing A-level chemistry resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make A-level chemistry a walk in the park.